Raw code often contains inconsistencies that break traditional generators. We need a pipeline that identifies these issues and adjusts itself automatically. We are going to build a system to handle that. In the next 6 minutes, we will set up a code generation pipeline using Python, Llama, and XSLT. This setup uses stateful execution loops and context management, patterns observed in agentic command line tools like Anthropics Claude Code. By adding a self-healing loop, local development becomes more resilient, allowing the system to recover from errors that would normally require manual intervention. Step 1 is the Python environment. We'll use it to instantiate our local large language model through Llama. We establish 3 separate Asyncio instances to manage our data flow: the raw vector queue, the retry queue, and the success queue. Isolating these tasks into distinct queues prevents a single corrupted file from stopping the entire process. Each transformation runs as an independent task. Our architecture relies on a specific data shift, moving away from rigid, nested XML schemas. Instead, we extract a generic key-value pair from the abstract syntax tree. This stable KVP format remains consistent even if the codebase changes. Decoupling the data extraction from the final target schema helps avoid the brittleness that typically causes automated generators to fail. Once the data is in the KVP format, we pass the XML to Llama to generate our XSLT transformation script. To ensure accuracy, we prompt the AI with a strict playbook. Looking at this UI, you can see the rules requiring the model to use XSLT 3.0, which prevents common engine version errors. We also instruct the AI to use text value templates. This replaces verbose tags with simple curly braces, making the style sheet easier to debug. The Python script then executes the transformation, applying that generated XSLT against our original KVP data. This process converts the generic input into the specific, highly structured C# or TypeScript code required for your target application. Using a playbook to control the AI's output ensures that the transformation layer remains deterministic and stable across different files. Even with a playbook, an AI model will occasionally generate invalid XSLT or hallucinate a function. We protect the pipeline by wrapping the XSLT execution in a try-except block to intercept these failures immediately. If a compilation error occurs, like a namespace mismatch, the system captures the stdr string, which indicates a failure. The routing logic catches that error trace and diverts the task away from the main flow and into the retry queue. Now the self-healing begins. The system automatically reprompts Llama by feeding the exact error message back into the model along with the original KVP data. The AI analyzes its own stack trace, identifies the syntax error, and attempts to patch the XSLT script for a second compilation attempt. When the patch succeeds, the file moves out of the retry loop into the success directory. This closed-loop error correction allows the generator to handle unexpected syntax errors autonomously, maintaining progress where a standard script would stop. You have now built a localized, self-healing code generation pipeline. The success directory now holds both the dynamically generated XSLT and the final output code, verified and ready for use. This baseline can be scaled by feeding it broader data sources, such as converted GitHub repositories or scraped API documentation. Use this orchestration pattern to handle complex tasks like multi-file refactors or automated code-base migrations. In an AI-assisted environment, true leverage comes from engineering systems that can autonomously identify and repair their own errors.